Start. Welcome back. This is Selection Hour. This is a very interesting segment of the crash course. We'll be doing questions from whatever we studied before this. So we talked about group 13. Now here in the Selection Hour, I have a few questions for you from the previous year NEET papers as well as a few other interesting questions which will tell you how to go about solving a question when you are attempting your paper. We'll start with the first one. I'll read this question. Good evening. Taking stability as the factor, which one of the following represents correct relationship? Any ideas? Read the question. Any ideas how we can solve it? Bunty and Prachi? Anand Royal? Any clues? So how do you see if a given compound is stable? You look at the first one, aluminium chloride, AlCl3, and this is AlCl. So you see the oxidation state. TLi, TLi3, TlCl3, TlCl, and indium I3, indium and I. So what is happening here? We're talking about the oxidation state of +1 and +3 in all these. Now these are group 13 compounds, right? So what have we spoken about? The inert pair effect comes into play here. Inert pair effect says that as you move down the group from boron, aluminium to thallium, the stability of +1 oxidation state increases. So now which out of these will be the most stable? +1 of aluminium will definitely not be stable. Here we are talking about +1 of thallium and +3 of thallium. We already know that thallic iodide does not get formed. So this appears to be a correct answer. Again, here they are saying +3 of thallium is more stable than +1. This is also wrong. Here they are saying +3 of indium is more stable than +1 of indium. So this is also not true because indium falls below. So +3 oxidation state tends to get destabilized. So correct answer here would be thallus iodide is more stable than thallic iodide. This is the correct option. Did you get it? Let's move on. Next, BF3 is planar and electron deficient compound. Hybridization and number of electrons around the central atom respectively are. So here we are talking about BF3. Boron is the central atom. It is a group 13 element. Atomic number is 5. Configuration would be 1s2, 2s2, 2p1. To form BF3, the electron will have to be excited from the 2s shell to the 2p, and this is the excited state electronic configuration that we get for boron. Now, since 3 fluorine atoms are present, one electron from each fluorine atom forms a bond with boron. It is utilizing s orbital and 2 of the p orbitals here. So this is sp2. Alright. What is the question? What is the hybridization? So hybridization in BF3 would be sp2, and sp2 is a planar structure, triangular planar, because 2s orbital, 1 s orbital and 2 p orbitals are being used. So this is sp2. And what is the number of electrons? When we talk about the number of electrons around the central atom, we are implying the valence electrons. So 3 electrons were from boron, then each fluorine gave 1 electron. So this is what is BF3. That means the total number of valence electrons around the central atom are now 6. The correct answer is sp2 and 6 here. And this also is telling us, if you remember from our class, that boron BF3 is an electron deficient compound because the electrons around the central atom are 6. Next. Now, the correct order of atomic radii in group 13 elements. This also we have just discussed. So ideally, if you have a group, this is group 13, boron, aluminium, indium, gallium, thallium. Alright, So moving down the group, more shells are getting added. So ideally the atomic radii should increase, but an anomaly is observed here. So instead of, sorry, gallium, indium, thallium. Okay, so ideally it should be increasing down the group, but an anomaly is observed here. So atomic radii of aluminium is not less than gallium. That of gallium is less than that of aluminium. So this is the correct order. So out of these, how will you see? Expected would be this. This is the expected order. Anomaly is here. So you will change this. Gallium is less than aluminium. And now if you rearrange them, we can write this as indium and thallium, stating that that of gallium is less than that of aluminium. So this is the correct answer. Look for it here. D. Option D will be the correct option. Yes, non-2 power of fact, you got it right. No, it is D. Correct option is D here. All right. So it is not C. That of thallium is the largest. Moving on. Okay, the stability of +1 oxidation state among the group 13 elements increases in the sequence. This is again a very simple question. Please give me the answer quickly. Which concept are we going to use here for the stability of +1 oxidation state? Yes, can I get an answer? We'll be using the inert pair effect on going down the group. The stability of +1 state increases, so the order would be this one here, A. Yes, you got it right, inert pair. Good, good. Moving on. All right. Which one of the following elements is unable to form Mf6 3- ion? It's again very interesting. We already discussed it in the class. Can you try? Anybody? So the covalency of the element here is 6. Okay. So out of gallium, aluminium, boron and indium, which one cannot expand its covalency? Which one has an anomalous behavior? Do I get an answer? The power of fact says A, Varshini says A. Yes, you are right. Gallium is the answer, because gallium cannot expand its covalency beyond 4 because of absence of d orbital. So this question is directly from the anomalous behavior of the first element in the group 13 elements. Good. Moving on. Now this is interesting. So this is a concept which I did not discuss in class deliberately. So we'll do so now. The tendency of BF3, BCl3 and BBr to BBr3 to behave as Lewis acids decreases in the sequence. Now what is happening here? Let's talk about the trifluoride of boron, BF3. Okay, now why is it behaving as a Lewis acid? We already discussed. It has 3 valence electrons. 1 electron comes from fluorine each, so total valence electrons is 6. This is not a noble gas configuration, and hence BF3 is an electron deficient compound. Let me Rishabh. Boron hoga. Yes, boron is right. Boron is the answer. I'm sorry, I meant to say boron. Boron is the answer. Sorry. Right. Now, okay, coming back to this. what happens now? BF3 is an electron deficient compound. It behaves as a Lewis acid. So it has 3 bonds, 3 single bonds, but it has been found that the bond length of these BF bonds is much smaller and the bond is very strong. So what is it that BF3 is doing to remedy its electron deficiency? So let us write the electronic configuration again. For boron, we have 2s and 2p. Okay, these are hybridized as sp2 orbitals in a triangular planar structure and form bonds with fluorine. Okay. Now there is one orbital empty here. So what happens in trihalides of group 13 elements, especially for boron? Now F has lone pairs of electrons. So F has a full pz orbital. So pz orbital of fluorine contains 2 electrons and the pz orbital of boron here is empty. So pi back bonding or pi dative bonding takes place, and the pz orbital of fluorine donates its electron pair to the empty pz orbital of boron, which is perpendicular to this plane. So we have a plane of BF, 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 it's a triangular plane, and the pz orbital, which was empty, is perpendicular to this plane. Now fluorine has filled pz orbital. It donates its 2 electrons from the pz to the empty pz of boron, and this is called pi back bonding or pi dative bonding. Because of this, the BF bond attains a double bond character, okay, and it remedies its electron deficiency. Now the question is the tendency of BF3, BCl3 and BBr3 to behave as Lewis acid, means how electron deficient are these. So you have to arrange them in an order. So BF3 conveniently forms pi back bonding, but when you move on to chlorine and bromine, the size of chlorine and bromine increases, right? That means that effective bonding does not take place. Effective back bonding does not take place. So BBr3 has to be the most strongest Lewis acid, followed by BCl3, followed by BF3. The correct answer is B. Did you get it? No. Alright. So the correct answer is BBr3 is the strongest Lewis acid because the pi back bonding, which is making the molecule less electron deficient, is not taking place that effectively because bromine is bigger in size, followed by chlorine and then fluorine. So the correct answer here is B. BBr3 is the strongest Lewis acid and then BF3 is the weakest of all, if you compare these 3 here. Alright, take a minute, look at this concept. Alright, yes, you got the answer. Moving on. Next, boron compounds behave as Lewis acids. This is a very simple question. Please give me the answer. Read the question and give me the answer. Boron compounds behave as Lewis acids because of their ionization property, electron deficient nature, acidic nature or covalent nature. What is the answer? Yes, B. You got it right on to B, electron deficient nature. We've just discussed they behave as Lewis acids because of electron deficient nature. Right. Which of the following statements is not correct about diborane? Alright, so we were not able to discuss diborane. Let me quickly talk about its structure so that you are able to answer. Okay. Diborane is B2H6. It is the simplest of the boron hydrides. Now the structure of diborane is of a great interest. It is an unusual structure. So what happens? we have 2 borons, 6 hydrogens, okay. 2 borons will give us 6 electrons, and we have 6 hydrogens which are giving us 6 electrons, giving us 12 valence electrons in all. Now these 12 valence electrons are not sufficient to form all the bonds required. That means it is again an electron deficient molecule. What is happening here? We have boron which has normal covalent bonding with 2 hydrogens here. The other boron also has normal covalent bonding with 2 hydrogens here. But these 2 borons are not sp2 hybridized, like in the case of BF3 or BCl3. These are now sp3 hybridized. And they form bridge bonds. So hydrogen bridging takes place, and we have bridging bonds with the remaining 2 hydrogens. So these 2 BH bonds here and these 2 BH bonds here are normal covalent bonds, and these bonds here BHB, BHB are bridging bonds, or they are also called banana bonds. Now these bridge bonds are perpendicular to the plane, and these lie in a plane. So BHH, BHH lie in one plane, and the bridges are perpendicular to the plane. And this boron is sp3 hybridized now. Okay, now let us look at the options. There are 3 center 2 electron bonds. This is correct. Why? Because if you look at this bridging bond here, now boron is giving 1 electron, this boron is giving, this hydrogen is giving 1 electron here, 1 electron here. These 2 electrons are shared between these 3. So 3 centers BHB and 2 electrons. Similarly, now this boron is forming a bridge with this hydrogen and this boron. This boron gives 1 electron, this hydrogen gives 1 electron. This has already given its electron here to this hydrogen. So this complete bridge again has 2 electrons in all, but 3 centers, 2 electrons. So they are 2 3 center 2 electron bonds, which is correct. Now the 4 terminal BH bonds are 2 center 2 electron bonds. That is again true because these are normal covalent bonds. Option C is the 4 terminal hydrogen atoms and the 2 boron atoms lie in one plane. So this is again true. We have just spoken about it. Yes, the correct option, Rishabh, you are right. It's D. Varshini, yes, it is D. So both the boron atoms are not sp2 hybridized. In diborane, they are sp3 hybridized. So D is the correct option. Perfect. Moving on. Boric acid is an acid because its molecule. Alright, so boric acid is H3BO3. Now, if you talk about boric acid, you will see it is not a protonic acid. It does not give a proton. But what it does is, it is better written as BOH whole thrice upon reaction with water, H2O, because all plus compounds of boron, where boron is in a +3 oxidation state, are electron deficient. This would want to take away a pair of electrons from water, so it takes away an OH minus ion from water. What happens? So it forms the tetrahedral complex BOH4 minus, and it furnishes a proton. So this is how hydroboric acid, orthoboric acid, acts as a weak acid. It does not furnish a proton, but it takes away an OH minus from the water and then gives a proton. This proton in water is obviously present as hydronium ion. Right? So it partially hydrolyzes in water. Right? So the answer is it accepts OH minus from water, releasing proton, correct. So it does not give up a proton, it does not contain any replaceable H plus, and it does not combine with proton to form water molecule. So correct option is C. You got it correctly. Yes, Rishabh and Masarat. Yeah. No, Masarat, it is not A. The correct answer is C. It accepts OH minus because it is an electron deficient compound and furnishes a proton. Right. Moving on. Aluminium becomes passive in nitric acid. This we have done in the class. Can anybody answer? Nitric acid is an oxidizing agent and aluminium becomes passive. Why? Can I have an answer? No, it is not C. It is not C. It becomes passive in nitric acid because it forms a thin film of oxide. Nitric acid is an oxidizing agent. Yes, the answer is B. It forms a thin film of oxide. Moving on. Okay, Al2O3 reacts. Now here the concept of the type of metal oxide. So metal oxides, non-metal oxides and amphoteric oxides. Aluminium is amphoteric in nature, so it reacts with both acids and bases. So Al2O3 reacts with HCl as well as NaOH. This is the answer. Right, borax bead test is responded by. Borax bead test, what happens in a borax bead test? Have you given the answer for this one? For borax bead test, can you give the answer? Upon heating, borax first loses water molecules and then on further heating, it forms sodium metaborate, right? And boric oxide. That sodium metaborate, when borax is heated with another metal oxide, it forms colored metaborates, which helps in identification. Yes, so the correct answer is D, metals which form colored metaborates like cobalt. Alright, yes, D is the answer. Moving on. From the following, the compounds that react with BF3 are. Okay, this requires application. If you see BF3 anywhere in your paper, the first thing would be that BF3 is electron deficient. BF3 is electron deficient, yes. So it would want to take a pair of electrons. Can ethers give a pair of electrons? Yes, because ethers have the formula ROR. So oxygen has 2 lone pairs. It can donate. H2 also has lone pairs which can be donated, and NH3 ammonia also has lone pairs. Yes, so whatever answers I am getting, D, Varshini, Komal, non-2, yes, the answer is D, all of the above, because BF3 is electron deficient. Alright, aluminium chloride in acidified aqueous solution forms a complex A. The formula of A in hybridization of aluminium. This is again a very easy question. Can I get the answer for this? What happens when AlCl3 hydrolyzes in water? Aluminium can expand its covalency, so it will form Al3 plus ions. Al3 plus ions will be hydrolyzed H2O6 3 plus. Alright, so this is the complex that is formed. Now what is the hybridization? Aluminium has empty d orbitals. No, the answer is not D. We discussed in the class, it is sp3d2 because 3s, 3p and then 3d. Talk about aluminium. So Al3 plus has this configuration. So one water molecule donates electron pair here, 3 here and 2 here. sp3d2. Right. So the answer is A. Yes, it is A. Next, a strong oxidizing agent among the following is. This is an interesting application of the inert pair effect. Inert pair effect. Right. So if something is an oxidizing agent, in itself it would get reduced. So if something is in a +3 oxidation state, it would get reduced to a +1 oxidation state. Only a compound which prefers to be in a +1 oxidation state would be a good oxidizing agent, right? Now can I have an answer? These are group 13 elements. Which out of these would prefer to be in a +1 state, would prefer to get reduced and hence act as good oxidizing agents? Right, A is the answer. Thallium. Because as you move down the group, the S electrons are not participating in bonding and the +1 oxidation state becomes more stable. Next question. White fumes appear around the bottle of anhydrous AlCl3. Now this is again something we have done. Can I have the answer for this? What happens when AlCl3 in a bottle is kept, white fumes appear? What exactly is happening? What are the white fumes? Think again. Now AlCl3 partially hydrolyzes with the water vapor that is present in the air. So it gives HCl, and moist HCl gas, it appears white in color. So the answer is C. Hydrolysis of AlCl3 gives HCl gas. Is this clear? Moving on. Orthoboric acid when heated to red hot gives, okay. So orthoboric acid is H3BO3 on heating to around 100 degrees Celsius. I am doing this because this reaction is something we could not discuss in the class. Orthoboric acid when heated to 100 degrees Celsius gives metaboric acid first, and on further heating it gives us B2O3. So B2O3 is also called the anhydride of orthoboric acid. It is boric oxide and it is also called boric sesquioxide. Sesquioxide is half an atom of O is present, so MO half, which would essentially mean M2O3. Okay, so B2O3 is formed when it is heated to red hot. So the correct answer is boric anhydride, because B2O3 is also the anhydride of orthoboric acid. Now the answer here is D. Because the question says red hot, it does not say heating to 100 degree, 120 degrees Celsius. Okay, metaboric acid is formed when you heat it to 100 degrees Celsius. Alright, so the answer is boric anhydride. Moving on. Consider the following reactions. So aluminium is reacting with NaOH to give us X and H2, and diborane B2H6 is reacting with ammonia to give us a compound Y. What are X and Y? So in NaOH, aluminium gives NaAlOH4. Okay, Na plus AlOH4 minus this sodium aluminate and hydrogen. The other reaction is diborane reacting with ammonia and on heating with NH3. So diborane, when it reacts with ammonia, first it forms an ionic complex which is somewhat like this: BH2 NH3 . Right. So when diborane reacts with ammonia, with excess of ammonia, we get this ionic complex, which on heating gives us a very, very interesting molecule which is called borazine. So borazine is B3N3H6. We'll talk more about borazine. There's another question coming up where we will talk about the structure of borazine. So the answer here would be this one here. So we have sodium aluminate and borazine, N3B3H6. So X is NaAlOH4, Y is N3B3H6. This is the answer. It's B. No, take a look again. First, aluminium is reacting with sodium hydroxide, and in the next reaction, diborane is reacting with ammonia. Fine? It is B. Next, a compound among the following that is least likely to behave as a Lewis base. This question is extremely easy. I want you to attempt it, please. Here we are talking about a Lewis base now, so don't be confused. We are not talking about Lewis acid. We are talking about a Lewis base. A Lewis base is a substance that donates its electron pair. What would be the answer? Can I have an answer? B. Nonto, it is correct. It's B. BF3. BF3 cannot act as a Lewis base because it is a Lewis. Yes, Varshini, it is B. BF3 is the answer. Because it is electron deficient, it will act as a Lewis acid. Here is an assertion and reasoning question that is very interesting, and it comes up many a times in the NEET paper. You should know how to attempt it. Okay, let us read these. Now, the total number of coordinate bonds and covalent bonds in borazine is 3 and 12 respectively. That is the assertion. Assertion is a statement. So, you are putting forward a statement and saying that it is true. If a statement is true, this means it should have a reason. Now, the reason that they are giving here is its structure is similar to benzene. Now, before you try to answer, let me explain the structure of borazine. So, borazine is B3N3H6. Alright, we have alternate boron and nitrogen, which are arranged in a hexagonal arrangement like this. Okay. To every boron and to every nitrogen, a hydrogen is attached. Now you see, every boron has three bonds, nitrogen has 3 bonds, boron has 3 bonds alternatively. So it's a hexagonal ring. What they are saying is total number of covalent bonds is 12. So if you count the covalent bonds, they are 12, right? 6 in the ring and 6 outside the ring. And then there are coordinate bonds. Because nitrogen has a lone pair of electrons, it can donate this lone pair to boron, because any compound of boron would be electron deficient. So this lone pair gets donated and a coordinate bond is formed. Similarly here and here. So this is also correct. Covalent bonds are 12 and coordinate bonds are 3. This is the structure of borazine. Now the reason that its structure is similar to benzene. Do you think this is the reason that the structure is similar? No, the structure is similar to benzene because one, it is a hexagonal ring, then there are delocalized electrons because they are alternate double bonds, they are delocalized electrons, and it is aromatic. Its physical properties are also similar to benzene. The structure of benzene is this, hydrogens, right? So the assertion is correct. There are 3 coordinate bonds and there are 12 covalent bonds. But the reason for that is not correct. Its structure is similar to benzene. This is not correct. So the correct answer would be the assertion is true, but the reason is, this is not the reason for this particular assertion. Okay, both the statements are true. Its structure is similar to benzene, but this reason is not true for this particular assertion. All right, moving forward. Sorry, yes, you are right. No, Rishabh Mitra, you are right. So the both, what I said was both assertion and reason are true, but the reason is not the correct explanation for the assertion. Sorry, yes. So the answer is B. Both are true in themselves, you are very right, but reason is not the correct explanation. Good, moving on. Again, another assertion. Bx bond length, this is B. Bx bond length in BX3 is shorter than the expected value. The reason that they are giving is p pi back bonding that occurs between B and X. We just discussed this. If you talk about BF3 also, there is pi back bonding. Pi back bonding takes place to remedy. There is a comment, WhatsApp community not working. I'll ask the technical team to work on it. Okay, so there's pi back bonding, and hence this BF bond length is shorter than a normal single bond length, right? So assertion is this, and the reason is also correct. So the option would be both assertion and reason are true, and the reason is the correct explanation of the assertion. Yes, A is the answer. Right, Rishabh, you are correct. Moving on. BCl3 has a higher stability than TLCl3. This is again a question about the inert pair effect. What would be the answer? I am reading out the options. The +2 oxidation state of thallium is more stable than the +2 of boron. Okay, so +2 is ruled out because boron and thallium do not show +2, right? What would be the answer? Option C and D are talking about the +3 oxidation state. So option 3 and D are making more sense, right? So the +3 oxidation state of boron is more stable than the +3 oxidation state of thallium. That is correct. Yes, I have got the correct answer. Hania, Varshini, Nontu, Rishabh, yes, all of you are correct. So the +3 oxidation state of boron is more stable than that of thallium, because for thallium the +1 state becomes progressively more stable when you move down the group. Next, a compound X of boron reacts with ammonia on heating to give another compound Y, which is called inorganic benzene. The compound X can be prepared by treating BF3 with lithium aluminium hydride. Lithium aluminium hydride. The compounds X and Y are. So inorganic benzene is borazine, which we just discussed. So which compound of boron reacts with ammonia on heating to give borazine, inorganic benzene? We have a compound of boron which is reacting with ammonia. Which compound reacted with ammonia? Diborane. So diborane is X. It reacts with ammonia to give this. Now it can be prepared by treating BF3 with lithium aluminium hydride. So if we have BF3 with lithium aluminium hydride, a very interesting way to remember this, it's just a way. So since lithium aluminium hydride is a reducing agent, you can say that it adds on hydrogen to boron, so you get diborane, and then you have lithium fluoride and aluminium fluoride. This is the reaction. So compound X would be B2H6 diborane and Y would be borazine. So B2H6 and B3N3H6. So correct option is A. Yes, you got the correct answer. A is the correct option. Moving on. An element that cannot form MF63-. This is a repetition. We already know it's boron. Boron is electron deficient, so it cannot, and it does not have d orbitals. So it can maximum form a compound with a covalency of 4. It cannot go beyond that, and hence it cannot form MF63-. So the answer is boron. Next, another assertion and reason question. Boron always forms a covalent bond. Reason, boron has a diagonal relationship with silicon. Alright, So first assertion, let us see if the assertion is correct. Boron always forms covalent bonds. We discussed it. If you attended the last class, you will see that boron has a very high ionization energy, right? And the sum of the first 3 ionization energies. So if you have to form an ion out of boron, hypothetically it would be B3 plus, right? That would mean you're removing 3 electrons. So the sum of the first 3 ionization energies for boron is very high. And also if you say B3 plus is getting formed, it is an ion of a very small size and a high charge. Small size and high charge. If you talk about Fijan's rule, go back. Small size and high charge favors covalency. So, because it is very difficult to completely remove 3 electrons from boron and it has a small size, covalency is favored. So, the statement that boron always forms a covalent bond is correct. Boron always forms covalent bond. The reason behind that, the reason that they have given in the question is that boron has a diagonal relationship with silicon. Now, you've read about diagonal relationships, right? But this is not the reason. The statement is correct. Boron has a diagonal relationship with silicon, but it is not the reason for the given assertion. The reason for this given assertion is high ionization energy and small size. So the correct answer, have you given the correct option? Rishabh, you are right. Yes, it is B. Both assertion and reason are true, but reason is not the correct explanation of the assertion. So correct is B. This is a correct statement, but it is not the reason why boron forms covalent bonds. That is why option B is the correct option. Alright, the BF bond lengths in BF3. So we have BF3. The bond length here is 130 picometer. And in BF4, talk about BF4, it is 143 picometer. They differ why? Now going back to BF3, since BF3 is an electron deficient compound, pi back bonding takes place. Pi back bonding takes place in BF3 and the bond length acquires a double bond character. Double bond character and it shortens. Here boron is sp2 hybridized. It is a planar structure and back bonding takes place. Alright, in the case of BF4 minus, what happens? Now there are 4 bonds to this boron. So it is no longer sp2 hybridized. It is sp3 hybridized first of all. And since another fluorine has come and bonded to this boron, that is, it has given its electron pair to boron and formed a 4th bond. Now boron is no longer electron deficient. It is no longer electron deficient, so no pi back bonding takes place. There is no need for any back bonding, so no back bonding. If there is no back bonding, that means that these are all simple single covalent bonds. Single covalent bonds. Now let us look at the options. First says presence of triple bond character in BF3, that is wrong. B says resonance in BF4 minus, no, there is no resonance. Third says presence of a double bond character in BF3. This is the correct option because there is pi dative back bonding or dative bonding in BF3. So correct option is 3. Right, you got it. Good. And now I think this is the last question. No, we are done. We are done with the questions. Great. All right, it was a wonderful, I had a wonderful time solving these questions with you. Thank you so much for being so responsive. I'll see you on Saturday now at 3:45. So we'll be continuing with group 13, which we left because of paucity of time today. So we'll be talking about borax in a little detail, orthoboric acid and diborane, and after that we'll start with group 14. Okay, thank you so much for watching.